Okay, let me make just two announcements before we start. Let me say that for those who are speaking at the meeting, the money that was promised is going to be available after 3:30. Okay? Okay, so when these two talks finish, you can go to the room 208 and get some money. Okay? For the other participants, yes, there will be money, but from tomorrow on. And another thing is that, so tomorrow, the bus that took people to Hotel Vermont is still there, and you can go there and pick it up if you want to go to another restaurant, Couve Flor, for instance. So if you want to go there for lunch tomorrow. It's a pleasure to present Susan Colley from Oberlin College, and she's going to talk on combinatorial determination of severity degrees.
Thank you. I want to thank the organizers very much for inviting me here, to Aaron and to Steve for having a reason for them to invite me here, to Steve for all the mathematics that he enabled me to do, and because without that I wouldn't even be here, and also the opportunity to have seen the world thanks to him as well. What I'm going to do today is actually work very much in progress with Gary Kennedy and Florian Bloch. It's a bit speculative in places, but it starts from something not so speculative, a very nice classical motivating question, which is simply to determine the number of plane curves of degree d possessing delta nodes that pass through the appropriate number of general points in the plane. That's nothing other than the degree of the severity variety. And when the degree is large enough, these curves, the curves that will be counted will be irreducible, so the severity degree coincides with the appropriate Gromov-Witten invariant, usually written in terms of degree in genus rather than degree in number of nodes. But this relation also enables one to think about this number of nodes as really a sort of cogenus number, and that will come into play when I talk about the more combinatorial gadgets that will be attached to the problem here. I think many of you know that it's been conjectured for some time that the severity degree would be given by a polynomial, at least when the degree is sufficiently large. This was taken up in Lothar Goethe's larger conjecture about enumerating plane curves in projective surfaces. And recently, results establish the polynomiality threshold, that is the number for the degree that will guarantee polynomiality. We have really a triple of results. Fobid-McCalkin just a couple of years ago established that at least if the degree is at least 2 times the number of nodes, we'll have a polynomial computation. That was improved by a factor of 2 by Florian Bloch as part of his thesis work. And then very recently this spring, Vivek Chanda and Steve have improved that still by a factor of 2. And that actually verifies one of Lothar's conjectures as well. I don't know if there's a Moore's law that will continue to reduce that threshold by a factor of 2, but I suspect not.
Almost certainly not.
So that's one side of the coin. Of course, the other side of the coin are the node polynomials themselves and producing those. And here are 3 classical results. We can do much better now, of course, but the screens get large to hold the polynomials for higher numbers of nodes, so I'll just abbreviate and point out that Israel Weincencher, I believe, is responsible for node polynomials in degrees 4, 5, and 6. And again, Ragni Pina and Steve for degrees 7 and 8, generalizing techniques that Israel was using. So here's my little happy birthday shout out, Steve. And then we're really, I believe, the state of the art in terms of calculation is up to 14 nodes, and that's, again, due to Florian Bloch and the combinatorial tropical approach to things. all of this can be framed in terms of some nice generating functions. So they're generating series for the severity degrees, which I'll really look at this way, but of course those can be phrased in terms of the node polynomials. And I'm also going to be interested in really the logarithm, the formal logarithm of that generating series, which I'll call script Q, and what these gadgets might be. And I believe part of Lotar's sets of conjectures are that these functions here turn out to be quadratic when the degree is large enough. And the goal of the project that we've been embarked upon is to try to understand why this should be quadratic in as elementary and as combinatorial a way as possible. So that means that here we are in Brazil, so we should be looking at tropical works. I suspect you all know what a tropical curve is, but there's one. That's a non-singular tropical conic. It's just a weighted graph with edges going west, south, and northeast, d of them in each of those directions, and a balancing condition that needs to hold at every vertex. And actually, these are the results of taking abstract curves and parametrizing them to get pictures like that. They're important because these are, of course, piecewise linear, very combinatorial, and Macaulkin's correspondence theorem of, I guess now about 7 or so years ago, tells us that we can determine the severity degrees, and more generally, that we can determine Gromov-written invariance by just enumerating these tropical curves instead, counting with appropriate multiplicities that can be determined in a straightforward and algorithmic way. But I'm quickly going to leave the pure tropical side of things, which is not to say I'm going to return to more temperate geometry, but instead something, again, more combinatorial that one can associate to tropical curves. So let me just show you with pictures. Suppose we have a tropical curve like this. So this is a tropical quartic. You can tell because of the 4 rays going in the special directions, and there's a weighted edge just for fun. We can identify floors and elevators on these. So the red pieces are the floors, the black are the elevators. So the elevators are just vertical edges, and the floors are the various connected components of the non-vertical edges, the union of the non-vertical edges. So we have 4 floors in that picture. And then we can associate to that picture something much simpler looking, a floor diagram, where what we need to do is first remove the unbounded edges, so remove the rays, contract what's left of the floors to a point, and then direct the vertical edges downward, and we get a directed floor diagram. So in this case, the picture looks like this. So we would associate to this tropical curve something much simpler with just 4 vertices, one for each floor, and edges going downward that correspond to the bounded elevators and preserving any weights that may appear.
What does the 2 mean?
Weight to edge, weight to...
There is a balance, you said.
Yeah, and the balancing condition would hold here, but it's all contracted away. So these are, of course, much simpler to think about. Usually you draw floor diagrams on the side to save space. So there's that floor diagram again with the vertices labeled. So I will always be using vertices in increasing order, left to right. Arrows will go left to right, and eventually they'll disappear when I lost patience drawing them into each of the pictures. So that's an example of a very simple floor diagram corresponding to that tropical quartic. To give you a proper set of definitions, so a labeled floor diagram is just a weighted directed graph on some vertex set indexed 1 to d. No loops, so these are acyclic graphs. We need notation to discuss the edges and to discuss the lengths of edges. But what makes a floor diagram are the following conditions. So we have a labeled floor diagram if, first of all, whenever there's an edge, it's always going, well, left to right in my picture. It always goes from a lower indexed vertex to a higher one. And then there's also a divergence condition that needs to hold. So every vertex in the floor diagram satisfies a condition that if you compute its divergence, that is, you look at the edges that leave vertex J and sum up all the weights of those edges leaving vertex J, subtract the sum of the weights of the edges going into vertex J, that's the divergence. That needs to be at most 1. Now, in fact, I've been a little quick here because it's not always the case that if you simply go from a tropical curve to a floor diagram in this way, you'll get all these acyclicity conditions to hold. However, if you impose some point conditions on the original tropical curve, the appropriate number, and configure it in a suitably stretched out vertical manner, then you can associate to that something called a marked floor diagram, about which I'll say more in just a minute, so that there's a nice bijective correspondence between the tropical curves and these so-called marked floor diagrams. And so to count tropical curves, one can instead count these marked floor diagrams. So, little bit more notation, terminology. The degree is just the number of vertices of the floor diagram. So I'm going to really leave the tropical world pretty much now, except in its vestigial form for the floor diagrams. The cogenus, well, the cogenus, when the floor diagram is connected, as in the picture that I just had, it's exactly what it ought to be. It's what would hold to agree with the genus. Where you take the genus of the underlying graph of the floor diagram when the floor diagram's connected. When it's not connected, however, there's something more complicated. You need the sum of the cogenera of the connected components plus a sum developed from the degrees of each of the connected components of a disconnected floor diagram. And then finally, one more piece of notation. The multiplicity of a floor diagram is just the product of the squares of the weighted edges, of the weights of the edges. Okay, so let me leave that up for a second. So cogenus is what it ought to be in the connected case, something else in the not connected case. So here are a couple pictures. So this is a picture of a floor diagram where we have all edges have weight 1. All vertices here have divergence 1, except for this last one. And so if you calculate the genus of this, you find out it has maximal genus, and therefore the cogenus will be 0. So this is really the floor diagram one would associate to a non-singular curve of degree d. On the other hand, here's an example of a reducible quartic. So it's got two conic, tropical conic components. And what one would associate to that would be this disconnected floor diagram, this very simple disconnected floor diagram. And clearly then the degrees of each of these components should be interpreted to be 2. And therefore, and they're non-singular conics. They're coming from non-singular conic components. So the 2 cogenera here is 0, but the cogenus of the entire floor diagram is going to be 4. So things are very different in the disconnected case. Okay. So now I want to return to the idea of marking a floor diagram because it is that really one wants to enumerate. So this is really due to Mikalkin together with Brugalet and also Fomin, Sergei Fomin. The way to compute the severity degrees is really enumerating not the floor diagrams themselves, but ones that have markings attached. So let me, again, sort of step you through pictures about how to attach markings. If you have a floor diagram such as the one we began with, this simple thing, here's what we need to do. First, turn the red vertices dark blue, then add some new vertices and some new edges directed rightward. So how many do you add? Well, you add enough new dangling vertices and edges so that you have divergence 1 everywhere. Right? So here, divergence 1, here, 2 going in and 3 going out if you count with the weight. So that's divergence 1. Well, this does not need to be, that also now is divergence 1, 2 going in, 3 going out. All right, so that's step 1. Step 2 is to subdivide every edge. Every edge from the original floor diagram, not these added edges, and preserve the weights when one makes those subdivisions. So those are where the red points now went. They went to subdivide every edge, and you get a new graph, d tilde. And then a marking of D, the original floor diagram, which doesn't actually appear on this screen, but it's just this first part without the light blue extra vertices. A marking of that floor diagram is this new graph with extra edges, extra vertices, and a linear ordering on those vertices that is consistent, that extends the original linear ordering of the vertices of the original floor diagram. So this was 1, 2, 3, 4. We have to stay consistent with 1, 2, 3, 4 going left to right. But of course, this would now be in between. 2 markings are going to be equivalent if there's an automorphism of this graph that preserves the original vertices of the floor diagram. So it doesn't matter how one orders these. Those would give the same marking that for that subdivision. In this case, there are going to be 6 inequivalent, different markings for this floor diagram, essentially because this point can be located in 1, 2, it could go after this 3, 4, 5, 6 places by swinging it around. These, of course, are all equivalent via automorphisms. So, pardon? Yeah, well, I'm thinking of you could locate this vertex there, and that would still give a ordering that extends the ordering of the original vertices. You could end the vertex here. This dangling vertex can be positioned before the red point, after the red point, after that dark blue point, and so forth, and sort of in between, filtered in between, and all of those give different markings. Sure. So nu of D is the marking number, in this case 6. Okay. So we can do this with pictures, but the theorem is that, in fact, the severity degree comes very simply by just taking a sum of this marking number of a floor diagram times that multiplicity. Remember, that's the product of the squares of the weights of all the edges. And you just sum over the floor diagrams of specified degree and cogenus. So this is not speculative. Clearly, then, the problem really is how to determine this marking number in some way other than drawing a picture and counting. The multiplicity is very easy given the floor diagram. And we're going to, this is typically done by associating still more simplifying graphs to the picture and counting those. So, that brings me to floor diagrams, from floor diagrams to what one might call long edge graphs, what I believe is also known as template collections. But I want to really just for now think of them as long edge graphs. So if we have a floor diagram, perhaps something complicated like this, I'm going to associate a new graph to that. So I'm going to create a new graph D prime by adding an extra new vertex and then some edges that make the divergence come out right at all of these points. Again, this is similar to the marking, but now we're kind of sucking everything into this last new vertex, so we don't have any dangling edges. Again, everything is ordered left to right. So divergence 1 here and here, so nothing's needed. Over here, we have 3 edges going in, but 3 edges coming out. So we're off by 1, so there's an extra long edge from this vertex to the to the new vertex. Here, I guess there are, this is, what, 2 going in, so I need 3 coming out. And so I need those 3 extra edges again, and similarly. All right, so that's step 1. Step 2 is simply to erase all the short edges. So short edges just mean length 1, weight 1 edges. So I keep that extra new vertex, but I throw away these short edges that I just put in, and retain and throw away these short edges that were there originally, and this one. But I do keep this one. Although that's only a length 1 edge, it's got higher weight, so we keep that. And now we have what we would call a long edge graph. Okay?
You don't do anything with the single vertices?
They're just sitting there for now. Eventually, yes, we'll mark things up again in another way, and they're not gone. But no, we don't erase them. So this process, of course, is reversible. One can start with something that looks like this, and then put the edges back and erase the vertex, and end up with the floor diagram. All right. So what's the definition? Well, our long edge graph is very simple. I'm actually, for mainly purposes of exposition, I'm really going to think of a long edge graph as actually being on all vertices with non-negative indices. So I'm going to actually think of it on an infinite set of vertices. It's a long edge graph if, first of all, only finitely many edges. So it's a finite graph in that sense. The edges all have positive weights, starting at 1, and no short edges. Every edge is either length more than 1 or weight more than 1. And so here's an example of another example of a long edge graph. It's just for purposes, again, of exposition, I'm really just going to throw in those extra vertices, and there are really a lot of vertices here, but really all that's of interest is right in there. Okay, so again, we can talk about multiplicity just as we have before. It's just the product of the squares of the weights of the edges. But now the cogenus is going to be defined a little differently, very easily to compute based on the long edge graph, and consistent with what we were doing with floor diagrams, that correspondence from floor diagrams to these kinds of graphs. This cogenus will agree with the cogenus we compute the other way. So again, if we look at this, this graph, it's evidently got multiplicity 36, and it's got cogenus 4. This is 1 plus 2 plus 1. Okay? So now let me say a word or two about allowable graphs. Suppose we have a long edge graph. Now I want to keep count of the sum of the weights of the edges that fly over each consecutive interval of vertices. So these are, count the weights of the edges that begin at vertex I or to the left of vertex I and end at vertex I plus 1, the next one, or to the right of that. That's what lambda sub I is. All right. Then a graph is going to be allowable for some positive integer if nothing's happening to the right of vertex D plus 1. If there are any edges that come into vertex D plus 1, they have to have weight 1. And then finally, we need this condition. We need I minus lambda I to be non-negative. And this has to do with markings that are about to come up. I need that number to be non-negative. Of course, if a graph is allowable for a particular value of D, it's going to be allowable for all values greater than that D as well. Okay. So I want to move towards, again, returning to severity degrees in some way. Suppose we have a long edge graph, we can create G prime simply by subdividing every edge in the middle and preserving the weights as we did before. Then we're going to say we have an ordering of that graph by taking an ordering of this subdivided graph that is an extension of the original ordering of the vertices, as we were doing before with floor diagrams. Now, if,
You do not want automorphisms here?
not yet, I haven't counted anything yet, so I'm just putting points in. If we have an allowable graph, we also, now we're going to put in what plays the counterpart role of markings. We're going to extend that graph by throwing in some short edges, edges that go between consecutive vertices, I and I plus 1. Again, it's done to make divergence equal to 1. We'll call that the extended graph. This is exactly how many edges you'll need to add over every interval. And so that's why we need this to be non-negative. Okay? And now we're going to subdivide that graph. And then an extended ordering will be an ordering of the subdivided extended graph that is consistent with the original ordering of all the vertices of the long edge graph before we added any extra points or extra edges. And we'll consider such extended orderings to be equivalent if now there's an automorphism that preserves the original vertices. Okay. And we'll take a number P of G that's going to count those different extended orderings. And it's interesting, this is independent of D provided you have an allowable graph. So this is not a function of D. But this next number is n of g. That is going to be a function of d in a kind of silly way. If the graph isn't allowable, we'll just say n of g is 0. If it is allowable, we're simply going to take this extended ordering number and multiply it by the multiplicity. Okay. So that's a function of d. And then the severity degree can be computed by just summing this up over actually just all long edge graphs of cogenus delta. Because these are functions of d, you'll get an expression that depends on d as well as delta. But what's nice is each value of d will only give you finitely many terms in this sum. So finitely many non-zero terms in this sum. Essentially because allowability forces a limitation on how many edges you can have. Okay. So I want to return to the generating functions we were looking at before, the generating functions for the severity degree and the corresponding formal logarithm of that series, and just refine those. And instead of taking x to the delta terms, instead just take the formal variables to be x to the long edge graph, x to the g. Add the formal logarithm where when one's expressing all these power series and multiplying graphs together, just take the disjoint union when you have a product like that. Okay, that'll still be a long-edged graph. So the generating series that one would normally look at, these original generating series, can easily be recovered simply by replacing the cogenus of the long-edged graph for G itself. All right. So let me show you a really simple calculation, how you'd get the very first node polynomial, okay, partly with pictures. So if you start with this generating series, you just need to get the terms in here that correspond to the graphs of cogenus 1. And there are really only two of those. This is the cyclops, because it's got one eye there. And this is the stub, because that's the shortest graph you can have here, but it has to be weight 2 since a long edge graph either has to have long edges or be of higher weight. But they could be located really anywhere. These single edges could be located starting at vertex k in both cases. So now what? So now we have to just compute, and we'll start with a trivial term, and then we'll have all these cyclopses moving to the right. And then we'll have stubs moving to the right. So all we have to do is figure out these n numbers, which require us to understand allowability plus whatever those marking numbers are. But fortunately, those are very simple graphs, so that's easy. The cyclops is actually the complicated one. So there's our cyclops. I want to subdivide this edge. I also want to add these extra edges, these extra short edges. So I'm going to want to have k edges in total, so I have to add k minus 1 here in this interval, and then I'm going to have to add k edges here so that I have k plus 1 in this interval. And these are all indistinguishable, but the red point really matters. So you can think of the red point as possibly being in the first interval here or the second interval over here. If it's in the first interval, it's one of these k points here, light blue and red, and so there are k places it could be located. If it's in the right half, well, there are k points here. This is one more, so this could be any one of the k plus 1 in total. So you get 2k plus 1, provided d is big enough. If d isn't big enough, then it's just 0. And then you do the same thing for the stub. That's even easier since there's just a single interval, but you have to count this twice. So you really only need to add k minus 2 edges here, because this one already counts as 2. So now you have k minus 1 points altogether. One of them needs to be red. There are k minus 1 ways to do that, and then you have to multiply by the multiplicity, which is 4, 2 squared. Okay? So that's it. Now you can start calculating. N1 is just the sum over all k of the Cyclops term plus the stub term. But those are actually finite sums because of allowability. Turns out you have to stop. And then it's easy. You just do the kind of algebra that the New York Times says we don't need to know anymore. And you get 3d minus 1 squared. It's kind of amazing. So the Cyclops and the stub were actually examples of templates, the very simplest sort of atomic long edge graphs that we wanted to look at, and actually that both Fomin McCulkin and Florian Bloch concentrated on. So what's a template? Well, if you have they're a special type of long edge graph, very simple. If you have a long edge graph, you can look at the right end, which is the last position where you have any edges. And you can think about internal vertices of a long edge graph. That's just any vertex between the 0 vertex and the right end. And then we'll say such a vertex is covered if there's an edge that flies over that vertex, meaning begins to the left and ends to the right. And then a graph gamma is a template simply when every internal vertex is covered. So the example I had before is not a template because vertex 1 is not covered, nor is vertex 2. But this is a template. Okay? All the internal vertices, in this case, if there are only 2 of them, they have edges beginning to the left and ending to the right. It's worth noting that whenever you have a template, you have to have an edge coming out of vertex 0, or you won't be able to cover vertex number 1. Along with templates, we have things that we like to look at that are nearly templates. They're just shifted templates. Every template has to have an edge coming out of vertex 0, but we sometimes want, as in the case you saw with the Cyclops and the stub, you sometimes want things to begin at rightward position. So you just look at shifted or offset templates, and you can say many of the same things. Every long edge graph can be decomposed as a union of offset templates in a unique way. Just every place where the long edge graph fails the covering condition, you split things apart. And this is what Bloch and Fomin and McCulkin would call a template collection for this reason. Also, given any positive cogenus, there are only finitely many templates that can have cogenus delta. That's just obvious from the way the cogenus is calculated. But it is worth noting that a template can't ever be allowable because vertex 0 has positive degree and that I minus lambda I condition automatically fails. However, you can always shift a template into allowability somehow. Okay, that's easy to see. There's a minimum value for k that you can use to shift. If you create a toggle that just notes whether all the edges on the right have weight 1 or not, then as long as you select an offset that's at least the minimum offset, you'll get an allowable graph here, provided d is at least this number. And that's important when we go back to the generating functions and the calculations of severity degrees. So first of all, if you have a long edge graph and it doesn't have to happen to be one of these offset templates, so it's not this simple graph perhaps shifted, then the Q of that G has to be 0. That Q, remember, comes from the logarithm of the generating series that we've refined into sorting out by long edge graphs. That's proved again by just splitting at a place where the covering condition fails and doing a calculation. But what this means is that whenever you have a template, if you define Q sub gamma of K as Q of its kth offset, then the proposition tells you that this refined Q function, which we define this way, summing over all long edge graphs, can just be a sum over templates where you count each offset. And then the nice thing is that this infinite sum is actually a finite sum because of allowability. It's just a sum from the minimum K to this number we had before. And that's very nice to know, because that puts the focus on this apparently simple function. Namely, we conjecture that this will always be linear, at least when K is sufficiently large. And that implies that if you sum this, well, ultimately this is going to be an expression that depends upon D. That will be quadratic. It's just essentially a discrete integral of a linear function in K. And so you'll get a quadratic function in D, at least if D is big enough. And then, of course, it would follow from that all the Q delta Ds have to be quadratic. So the focus then is just on how to understand this. The Q sub gamma K, where gamma is a template. And where we are with things is we actually are looking at some further refinements. So now, suppose you have either a long edge graph, or really we're interested in a template here, I suppose. Suppose you have not an ordering, but just are interested in what intervals you've placed the subdivision points. So you have all these edges, you subdivide each edge, and you're not so much concerned with the ordering of where those subdivision points are as much as the intervals over which you're putting them. So we'll call that distribution delta. Okay. And then we'll look at extended orderings that are consistent with that distribution. So now we look at orderings, but orderings that where the subdivision points are fixed over certain intervals that we might specify. And I'm going to call that P bar because I want to then really look at P, which is the number of truly different such orderings. And that depends on P bar together with a factor that's counting the automorphisms that fix that marking. Well, then you can refine the n number as well. Okay, still a function of D, 0 if you don't have an allowable graph, multiplicity times this particular ordering number. Okay. And then we can refine n bar and q bar to n double bar and q double bar, where instead of x to just a graph, we think of a pair now, of a graph together with the subdivision points of the original graph's edges, but only up to the markings of the intervals over which those lie. And so Q of G is just the sum of the Q's for the various distributions. And Q sub gamma will be, for a template, will just be Q sub gamma delta for appropriate subdivisions. So obviously, if we want to prove linearity of this, we could do it if we prove linearity of this more refined thing. So the Q sub template subdivision, but only up to the markings over the intervals. Okay, so that would be what we would like to prove. So let me show you a sample computation of all of this. So Q double bar comes from N double bar by a logarithm, and it turns out then that you can compute one of these very refined template with distribution functions by doing the following. Take a partition of the edges of the offset template into P blocks. So P is the partition of the edges into P blocks. And you get subgraphs. Those subgraphs will be long edge graphs. You get inherited subdivisions of the points of those subgraphs. Inherited distributions of the subgraphs. And then Q sub gamma delta will be the multiplicity divided by the number that counts the appropriate automorphisms of this. This just comes from the logarithm series. You would see a -1 to the p minus 1 over p, and then you would need a product of the graphs, the subgraphs that come from this partition. But if you want to count unordered partitions, you're going to have a p factorial, and so that cancels the p in the denominator from the logarithm, and you have an expression like that. And that's what you have to compute. So let me show you how to do that with a relatively simple case. So here is a cogenus 3 template, gamma. The multiplicity is 4, and the lambdas that count the edges over each interval are here, this 4 edges counted with multiplicity, and here just 2. Then there are 3 ways to do distributions. You can only subdivide this edge by putting a point in this interval, but you can subdivide these long edges in 3 ways. You could put the 2 subdivision points over the second interval. You could put 1 over the first interval and 1 over the second, or you could put both of those long edge subdivision points over the first interval. And again, I'm not really interested in the ordering per se as much as where those points are in terms of the markings. This will keep track of the automorphisms that respect these markings perfectly well. So I'll just compute for this distribution. Okay, so you have something that looks like that with edges A, B, and C. You add some extra edges in light blue, and you need to count something. So for this particular distribution, you need mu over alpha. You need p bar for the 1 block partition of those black edges. So that's the whole template. Then you have terms that come from the 2 block partitions. So you can either keep A and B together and C alone, or put A with C or B with C. The minus sign comes from the alternating sum that we have. And then there's one more possibility. You could have a 3 block partition where each edge is its own little subgraph. And you have to compute a product of those 3 counting numbers. But when you do those partitions, you have to think of each subgraph anew. So how many edges you're adding depends on how you're doing the partition. So just to really quickly do the first partition, this is where you're looking at the entire template. Okay, in the first interval, you can put this red point in any of k minus 3 places. Why? Well, if this is k, there are 1, 2, 4 edges, so I need k minus 4 edges. But now I have k minus 4 points here, one of which is k minus 3 points, excuse me, one of which is red, so that can be in any of k minus 3 places. Now here I'm going to add, let's see, this is k plus 1, so I want to have k plus 1 edges in total, so they're going to be k minus 1 light blue points plus 2 more, so k plus 1 in total. I can put one of them in any of the k plus 1 places, and then the next one has to be in one of the k that remains, so that's this falling factorial. Now, if you want to think of it as binomial coefficient, there's the 1/2 from the binomial coefficient. But we found that by writing things this way, you get monic polynomials inside, and that's very helpful to us. So that's when you compute this number. To compute the next ones, these 3, you do similar things, but you have to think of the subgraphs separately to do that. Okay? The only economy is that these 2 calculations are really the same, so that's why there's this factor of 2. And then in the last case, we need 2 times the marking numbers for each edge computed separately. So now you have these 3 cubic polynomials, and it's a miracle. It's all linear when you work it out. And if you do this for the other 2 ways of placing distributions of points, and sum those, you of course get linear things as well, and the total looks like that. So, what's next? Well, I'm going to leave you with a final conjecture. If you take this polynomial, and well, or what we hope will be a linear polynomial, and rewrite it a bit. So there's mu divided by alpha. If we rewrite this so that instead of summing over partitions, we really sum over the number of blocks as the outer sum, and then organize an inner sum over just the partitions with that many blocks, and write this as p bar of now gamma and p, still assuming that there's a distribution, but this is just shorthand. Conjecture C is just telling us that we have this sum that's linear in K. And it's really a finite sum. It just looks infinite. In fact, we believe that if you take this same term here and multiply by the Stirling number of the first kind and take that sum, it appears that you'll get a polynomial of degree m. But really all we have is numerical evidence for that. We don't have a proof yet, nor do we, unfortunately, have a proof for this. So if there's a lesson in all of this, it's that it's a lot easier to come up with conjectures than theorems. So thank you.